this video, we're going to go through some typical questions for a Calculus 1 final exam. If you're taking this course with me at Bellevue University, this follows along the final exam review sheet in your Blackboard course. If you are on YouTube finding this final exam review, I have linked that PDF review in the comments. The first question asks us to find the limits of 4 functions, and hopefully you have tried all of these before going through them with me. So it's not as beneficial to you if you just let me go through them. You should be trying them yourself first. So if you haven't done the questions on the review, stop this video right now, do the questions that you're able to do, and then come back to the video. For the first 2 parts of this question, hopefully you found them very easy because they're just polynomial functions. That means there's no points of discontinuity. So all we have to do is direct substitution. 2 squared is 4, plus 3 times 2 is 6. That gives us 10, minus 1 is 9. For the second question, same thing. It's a polynomial. 4 to the third is 64, plus 4 is 68, minus 1 gives us 67. Those two should be pretty straightforward. Now, if I look at the second 2 questions, if you'll notice, they're both rational functions, meaning they contain a fraction. Now, if I were to plug in 3 directly here, I would get 3 minus 3, which of course gives me 0, and I would get 9 plus 18 minus 27, which gives me 0. So it's indeterminate. So of course there's more than one way to solve or find the limit for an indeterminate function. I could use L'Hopital's rule, but in general, the easiest thing to do is to just do some factoring here. So notice I have to rewrite the limit as x approaches 3 because I don't get to get rid of that until I actually substitute the 3 in. So if I rewrite x squared plus 6x minus 27 in a factored form, that's x minus 3, x plus 9. So hopefully we're all remembering how to factor. And those 2 factors of x minus 3 will cancel. Now what does that mean? That means at the point x equals 3, our function has a hole. But the limit of the function still exists, and that limit would be 1 over 3 plus 9, or 1/12. So as x approaches 3, y approaches 1/12. And then for the second function, the fourth function, same thing. If I plug in 2, I'm going to obviously get a 0 in my denominator. So I'm just going to go straight to factoring. This is x minus 2, x minus 2. Oops. And don't forget to write the limit as x approaches 2, and then x minus 2. So obviously one of those factors will cancel, so this is now just the limit as x approaches 2 of x minus 2. So I'm going to get 2 minus 2, which is of course 0. So the limit is 0. Again, we would have a hole in that function, but we're not worried about the value of the function, we're worried about the value of the limit. Question 2 asks us to find derivatives. Remember, the proper way to denote that is just simply f prime of x, so f prime of x is sine of x. For b, I could either use the product rule, or I chose to rewrite f of x by distributing this is x to the 1/2, so I'm going to distribute that first. So this is 9x to the 1/2, and 3x to the, remember 4 would be the same as 8/2, so that's x to the 9/2. And now I'm going to take the derivative. So I'm going to have 9 times 1/2, or 9/2 x to the negative 1/2, and then 3 times 9/2, which would be 27/2, x to the 7/2. Now in terms of how well you're able to reduce that or write it in a better way, I chose to just simply take an x to the negative 1/2. So I know that each of these fractions has a 2, and I'm going to go ahead and put x to the 1/2 in the denominator. So for the first one, that's pretty easy. That just leaves me with 9. For the next one, you just have to kind of do the math in your head. If you've got 7 halves, but I'm going to be taking away 1, that means I'm back to 8 halves. So this is 27 x to the 8 halves, or x to the 4th. So that's how I would write it. But again, if you wrote it without writing it as one fraction, that would be just fine as well. For C, this is, remember, 2 things. So this is a product rule question. You have to use the product rule. So f prime of x would be the first times the derivative of the second. So 5x secant squared x plus the second times the derivative of the first gives me 5 tangent x. I'm not picky. If you want to take the 5 out of each term, you can. You don't have to. Let's continue on. For D, I have to use the quotient rule because this is a quotient. It's being divided. So the quotient rule says take the denominator times the derivative of the numerator, or bottom times the derivative of the top is the way that you've heard me say that. X cubed minus 5 times cosine of x. And then we subtract the top times the derivative of the bottom. So the derivative of the bottom is 3x squared, and then sine x. And the denominator is just the denominator squared. So just like that. And I don't have to do any more cleanup. For E, this is just a chain rule question. So remember, chain rule says go ahead and do the power rule. So 1/2 2x cubed minus 3x to the negative 1/2. And then the chain rule says now take the derivative of what's inside. So that's 6x squared minus 3. And then for this one, we are going to do a little bit of cleanup because we've got a fraction. So we've got the 2 in the denominator, and we also have all of this. So I've got the square root of 2x cubed minus 3x. And in the numerator, I would have 6x squared minus 3. Whether or not you factor out that 3 in the numerator, I don't care. And then for the last one, f prime of x, remember that this is really us saying sine x squared. So this is also chain rule. So it would be like 2 times sine x to the first, and then the derivative of sine of x is cosine of x. So you can either write it just as 2 sine x cosine x, or if you're really good at trig and you remember that identity, you remember that that's the same as sine of 2x. I will take either of those solutions. This next question is your typical rocket question. Or falling object question. So we are given the position function. This tells us the position or height of the rocket in this case at time t. We're asked to find 2 things: the time at which the rocket reaches the ground. So again, that means the position would have to be equal to 0. And then the velocity at that time. So we know that s prime of t will give me v of t. And so whatever t we solve for over here, we're going to then plug into this function. So let's get started. So the first thing we have to do is solve for t. So we're going to use the position function and set it equal to 0, negative 16t squared plus 32t plus 180. And now I'm just going to factor. You can use the quadratic formula if you are more comfortable with that. I like to factor. Oops. I get 4t squared minus 8t minus 45 just by factoring out the negative 4. And then I factor what's left over into 2t plus 5, 2t minus 9, and I find each of those t values. So this t value would give me negative 5/2 or negative 2.5 seconds. That one I don't care about. So you can just indicate that by crossing it out as I did. And I don't care about it because we don't care about negative time. And then of course the other one would give me 4.5 seconds. So that's the one that I'm going to end up caring about. So again, to answer the question, the rocket reaches the ground in 4.5 seconds. Now, I'm trying to find the velocity at that time, so let's find s prime of t, which is going to be equal to v of t. So I'm just taking the derivative of the position function, which gives me negative 32t plus 32. Now I'm going to find v of 4.5 because that's the time I care about. So if you think about this being 0, and this is 180 feet. So essentially what's happening is the negative 2.5 would be over here. So it's kind of this situation that we have going on. So don't be concerned that there was a negative. We only care about the positive 4.5. So I digress, back to the math, just making sure we understood exactly what was going on. So v of 4.5 means negative 32 times 4.5 plus 32. That gives me negative 144 plus 32, or negative 112. So the velocity of the rocket at 4.5 seconds is 112 feet per second. Why didn't I write the negative? The negative just indicates the direction, which means as it hits the ground, it's obviously going back towards Earth. So 112 feet per second moving toward Earth. Now we've got some implicit differentiation questions. Remember, when you derive something implicitly, that means you're deriving with respect to x. But if you have another variable like y, you're going to find the derivative as you normally would, but then you're going to include either dy over dx, or I just use y prime. So what I mean by that is, if I took the derivative of x squared, I would just get 2x as usual. If I took the derivative of y cubed, I think of it as though I'm deriving it with respect to y, which would be 3y squared. But because it's with respect to x, I would either write dy over dx, which to me is just too much work, so I just write y prime. And then again, what's the derivative of 4y? It would just be 4, but again, it's y with respect to x, so that's y prime. Then what we need to do is get all the y primes together, so I'm just going to keep 3y squared y prime on the left. I'm going to subtract 4y prime from each side and subtract 2x from each side, resulting in this equation. Now I'm going to factor out the y prime, so 3y squared minus 4. And then I want to get y prime all by itself. So y prime is going to equal negative 2x over 3y squared minus 4. Or for people who really don't like that negative in the numerator, I could write y prime as 2x over 4 minus 3y squared. I will take either. For my second question, again, if I would derive with respect to x, if I take a y, I just need to include the y prime. So the derivative of y is just 1, or y prime. The derivative of tangent of x is secant squared x. The derivative of xy, remember this is a product, so I'm taking the first value times the derivative of the second, plus the second value times the derivative of the first. Now let's get all of the y primes to one side, so y prime minus xy prime is equal to secant squared x plus y. Factor out the y prime, so that's 1 minus x, secant squared x plus y. So y prime is equal to secant squared x plus y divided by 1 minus x. Here's an example of a related rates question. So I've got a circle, and the radius is increasing at a rate of 4 centimeters per minute. So the change in radius with respect to time is 4 centimeters per minute. Find the rate of change of the area. So find dA, the change of area with respect to time, when the radius is 5. So r equals 5. So how do I do this? Remember, we start with the function area. So how do I find the area of a circle? Pi r squared. How do I then find the derivative? It's just like we just did with with implicit differentiation. We said, okay, we're going to differentiate, in this case, with respect to time. So a becomes a prime, or dA over dt. The derivative of pi r squared is pi and then 2r, but then dr over dt. So again, we had two variables, but both with respect to time, which is why we wrote them that way. Now we already know that this is what we're trying to find, so that's going to stay on that left side, dA over dt. And for pi, obviously is pi, and then 2 times r, so 2 times 5, because r, we're finding it at the moment when r is 5. And then dr over dt is 4 centimeters per minute. Now, if you have trouble with labeling, it's not a bad idea to write 5 centimeters and 4 centimeters per minute. So when I multiply it out, I get dA over dt is equal to 2 times 5 times 4, or 40 pi, and you can certainly multiply out the pi if you'd like. But then I've got centimeters and centimeters, so centimeters squared per minute, and that is my final solution. Now let's take a look at vertical, horizontal, and slant asymptotes for these functions. Remember, to find the vertical asymptote, it's when the denominator would equal 0. So not a bad idea to do any factoring first to make sure that there's nothing that's going to factor out. So for my numerator, I would factor out a 2x, and that would leave me with 2x squared plus 1. And my denominator, I would factor out a 2, and that would leave me with x squared minus 1, which would be x plus 1, x minus 1. So that's my factoring. I can see that nothing's going to cancel. So let's now take a look at when is the denominator going to equal 0. So when does 2 times x plus 1, x minus 1 equal 0? Well, obviously when x is equal to negative 1 and when x is equal to positive 1. These are the vertical asymptotes. In terms of horizontal or slant asymptotes, we're really looking at the limit as x approaches infinity of our function. So I'm going to go ahead and write that in the original form. And if you get a value when you do this, that's going to be a horizontal asymptote. So if you get the limit as x approaches infinity gives you some number, some constant, that's going to be a horizontal asymptote of y equals c. And if you get the limit as x approaches infinity as some function, then it's going to be a slant asymptote at that function. So for instance, in this case, we would really be looking at these two values, and we could see that that limit as x approaches infinity would reduce. 4 reduces with 2, so that gives me 2, on the numerator. And then x cubed over x squared gives me x. And so notice when I did that reduction, I ended up with a function f of x. So I have a slant asymptote at y equal to x. And I encourage you to pop into desmos.com and graph that function and graph the line y equals 2x and see that it is in fact a slant asymptote. For the second function, I'm going to do the same thing. So again, any factoring that you can do, obviously I'm going to be able to take out an x, so that's going to give me like x cubed plus 3 over 4x to the 4th. So that's not going to change anything. So that means to find the vertical asymptote, I just set 4x to the fourth equal to 0, so obviously x is 0 is going to be my my vertical asymptote. And then to find my horizontal asymptote, I'm going to find the limit as x approaches infinity of x cubed plus 3 over 4x to the fourth. So again, I'm looking at those terms that would make the most difference. And that would leave me with the limit as x approaches infinity of 1 over 4x. And if I think about making x bigger and bigger and bigger, it's going to be 1 divided by a bigger number, which gives me 0, which means my horizontal asymptote is y equals 0. So mistakes I see people make often is over here they would write y equals infinity, which obviously doesn't make any sense, or they forget that an asymptote is an equation. And so notice for the vertical asymptotes it's x equals, and the horizontal or slant asymptotes it's y equals. So buckle in because this one is a doozy. Let's go ahead and get started. We're trying to sketch a graph by finding a bunch of stuff. So this is kind of a long question. We're going to find intercepts, asymptotes, intervals of increase, decrease, of concavity, min and max, points of inflection, and so forth. So we're going to jump right in. The first thing that you should do is do any simplification on the original function that you can. We find that there's not a whole lot that we can do. We can factor a 2 out of the numerator. We can rewrite the denominator as x plus 1, x minus 1. And that's simply going to tell us about our asymptotes. It's going to help us find those asymptotes. So we're going to leave that right there for right now. Now let's go ahead and before we find anything, I'm just going to go ahead and do the work to find f prime of x and f double prime of x. And then we'll punch through the rest of it. So this is probably going to be the part that takes the longest, is to actually find the derivatives because we're dealing with quotients. So quotient rule says denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared, and then simplify. So that's going to give me 4x cubed minus 4x minus 4x cubed minus 4x all over x squared minus 1 squared, which gives me negative 8x over x squared minus 1 quantity squared. Now remember, what we care about here is when does f prime of x equal 0. And it's going to equal 0 when the numerator equals 0. So we're going to say that x is equal to 0 is going to be a critical number. And we'll leave that right there for now. Now let's find f double prime of x. So the derivative of this function. So again, the denominator times the derivative of the numerator, squared, times the derivative of the numerator minus the numerator, so plus 8x, times the derivative of the denominator, which would be 2x squared minus 1 to the first, chain rule, 2x, close parenthesis. And then over the denominator squared, so that's x squared minus 1 to the fourth power. Now what? Well, it looks to me like I've got an x squared minus 1 in all of the factors. So here's one factor, here's another, and obviously in the bottom. So I'm going to turn this into the first power. I'm going to get rid of this x squared minus 1, and I'm going to turn this into the third power. Now I'm going to do my simplification. So that's negative 8x squared plus 8. And then all of this, because the x squared minus 1 is gone, turns into plus 32x. And this is over x squared minus 1 to the third. That reduces to 24x, oops, this was x squared, sorry, 24x squared plus 8 over x squared minus 1 to the third. Again, when does this function equal 0? And that would be when the numerator is equal to 0. So is that ever going to work? No, because if I set it equal to 0, I would end up with a negative, and that's not going to give me a value for a possible point of inflection. Okay, so no possible points of inflection. So now from here, let's start doing the actual work. So that's all the stuff we had to do to get to this point. So A says find the intercepts. How do you find the intercepts? Well, the x-intercept occurs when y is equal to 0. So when would 2x squared plus 2 equal 0? Never. No x-intercept. The y-intercept occurs when x is equal to 0. So we're going to say y is equal to 2 times 0 squared, which is 0, plus 2 over 0 minus 1. So that gives me negative 2. So my y-intercept is 0, negative 2. B, asymptotes. So we already did the work for the vertical asymptotes. So we're going to say vertical asymptotes because we've factored here would be at x equals 1 and x equals negative 1. We know they're asymptotes because they didn't get canceled out at all. And then we think about the horizontal or slant asymptotes, and again we would look at it's going to be horizontal, the limit as x approaches infinity of just really the consequential terms, 2x squared over x squared, and that's going to give me 2. So remember to write that as y equals 2. So that's the horizontal asymptote. Then for C, intervals of increase and decrease, I find it easiest just to, we already know we're going to be using 0 and positive and negative 1. So negative infinity to negative 1, negative 1 to 0, 0 to 1, 1 to infinity. This is really all of the work I need from you. Plug in the values in your calculator. I don't even need to see what the values are. And then we can see that this goes from increasing then to decreasing, so the point at 0 must be a max. So that will help us when we get to mins and maxes. For D, I'm doing the same thing, negative infinity to negative 1, but notice I didn't have any points of inflection, so I don't have to use 0. So I've got negative infinity to negative 1, negative 1 to positive 1, and positive 1 to infinity. And again, just use your calculator to find those values. For E, mins and maxes, we know that there's only a max, so I don't need to show any further work for that because I can see based on the table there is a max there. And so the max is going to be at f of 0, and f of 0 gives us negative 2. And so the max is at 0, negative 2, max. And then we have F, points of inflection. We already talked about the fact that there's none, so don't get confused just because we can see that it goes from concave up to concave down to concave up. Obviously, those are broken up by our asymptotes, and that's why they change, but they're not points of inflection. So a really rough sketch of this would be, go ahead and draw in your asymptotes. Now I know that there's no x-intercept, there's a y-intercept at negative 2. So in that first section, we're looking at increasing all the way to -1, so that's the first section, and concave up. So that's going to look like this. For the middle section, we're increasing up to 0, so we're increasing up to that point that we've already plotted, and then we're decreasing after that. And then it is concave down the whole time. And then for the last section, we're looking at 1 to infinity is decreasing and concave up. So it's going to look like this. Next question is an optimization question. I encourage you to draw a picture. It says we have a wall. We're going to draw a fence. And we're going to use 120 feet of fencing. So obviously one side will be called X and one will be called Y. And I'm looking for the largest area. So whatever I'm trying to optimize is going to be my primary equation. So my primary is going to be the area, which in this case is X times Y, whatever variables you use in your picture. The secondary will be whatever they give you in addition to the fact that you need to maximize area. And in this case, they're giving me linear footage. Okay, so we're talking about perimeter. So we're going to say the perimeter is equal to 2x plus y, because obviously there would be an x over here as well. So that's how much perimeter we have. Now, we're given that the perimeter is 120 feet. Oops, you don't need to label. And then we want to isolate one of those variables, and obviously it makes more sense to isolate y. So y is 120 minus 2x. That's my secondary. Then I'm going to start with my primary. Area equals x times y, and then I'm going to replace y with 120 minus 2x. So whatever I found using my secondary equation. I'm going to go ahead and multiply that out, 120x minus 2x squared. I'm then going to find the derivative of that. So that's 120, again, because I'm trying to optimize area. 120 minus 4x. I then want to find the critical numbers, so 0 equals 120 minus 4x. Add 4x to each side, divide by 4, x is 30. It's important that you show that x is actually going to be a maximum because I'm trying to find the largest area. So again, the easiest way to show that, 0 to 30, 30 to infinity. If I make my little table, plus minus tells me this is a max. And then of course I know that x is going to be 30, but what's y? Y is 120 minus 2 times x, which is 30. So 120 minus 60, which is 60. So the largest area I can enclose is 30 times 60, which is 1,800 square feet with dimensions, of 30 feet by 60 feet. So again, what is the area and what will the dimensions be? So I've answered both questions. Now we are switching gears from derivatives to integrals. So we're going in the opposite direction. Again, you may or may not need to use substitution. So for the first one, we do not. You should be writing that as f of x. So big F indicates that it is what you have found from the integral. So the integral of 2 is 2x. And the integral, which is the opposite of the derivative of cosine of x, is sine of x. Because it's indefinite, you should always use plus c. Same thing for b. No tricks on this one. Remember, this is kind of like the reverse of the power rule. So this is going to turn into a 3, but that means I have to divide by 3. So it's 6 divided by 3, or 2x cubed. And then same thing, this is 1, so it's going to turn into a 2, which means I divide by 2. 12 divided by 2 is 6, x squared, and then plus c. And you can always find the derivative of that to make sure that you did the integral correctly. For c and d, I actually am going to have to use some u substitution. So whenever you get anything too crazy, not a bad idea to set up a u. So u in this case is going to be 5 plus x to the 4th. Now why did I choose that? Because now I can call this u to the 5th. du is the derivative of u, which is 4x cubed dx. So I'm going to know that I need 4x cubed, so I'm going to put a 4 here, but if I put a 4 there, I have to put a 1/4 on the outside. So really, this is 1/4, and then the integral u to the 5th du, because 4x cubed dx has been accounted for, so that's what I'm finding. The result of that is 1/4, and then u to the 6th over 6th plus c, and then I simply sub the c back in. So 1 over 24, well, not 1 over 24, we're going to use 24 as the denominator, because 4 times 6, and then u to the 6th would be 5 plus x to the 4th to the 6th, and then plus c. I'm going to do the same steps for d. So u is going to be that function that's to the 4th power, so x squared plus 2. du is equal to 2x dx. Notice here I have negative 2x. I need it to be positive in order to fit the du pattern. So I'm going to multiply it by a negative, which means I need to move a negative to the front. So now I have negative integral of u to the negative 4th du. So again, everything inside that integral is either u or du. So to find the integral of u to the negative 4th, keep the negative on the outside. So u to the negative 4th is going to be u to the negative 3rd over negative 3 plus c. Well, obviously those negatives will end up canceling. So that's going to give me u to the 3rd, or x squared plus 2 to the 3rd over 3. Oops, I forgot it was a negative. I apologize. So I'm going to have 1 over 3, positive 3 in the denominator, and then x squared plus 2 to the 3rd, and then plus c. Question 10 asks us to find the integral geometrically. So instead of giving you a function, I'm giving you the picture of the function, which means, do you know how to find the area of geometric figures? And do you remember the order in which the integral should go, and that if the area is beneath the x-axis, then it should be negative? All of those things. So let's take a look at the first one. This goes from 3 to negative 2. Wrong order. So if I get something in the wrong order, it's negative 2 to 3 of f of x. So just keep that in mind, as I'm going to be finding the negative, and then I'm going to find the areas. So from negative 2 to 3, I've got one figure, which is going to be a triangle beneath the x-axis and a half circle beneath the x-axis. So for the triangle, again, it's beneath, so it's negative. So I'm going to write negative 1/2, and then base is 2 times height of 1. And then the circle is a half circle, but it's below the x-axis, so negative 1/2. And then the radius is 3/2, so pi times 3/2 squared. Now I've got a negative on the outside, and then I've got negatives on the inside, so I'm just going to positive all of that. 1/2 times 2 times 1 is 1. 1/2 times pi times 3/2 squared, which is 9/4, so half of 9/4 is 9/8 times pi, or 9 pi over 8. Just keep it like that. You don't even need to turn it into a decimal. For b, 0 to 1.5. So I'm looking beneath the surface, and it's 1/4 of a circle. So again, even though the values for my integral are in the correct order, it's going to be negative because it's beneath the surface. So negative, and then 1/4, and then pi times 3/2 squared, because it's a circle, pi r squared. And that gives me 9/4 times 1/4, so that's, sorry, times negative 1/4, so that's negative 9/16 pi, so negative 9 pi over 16. For C, again, this is in the wrong order, so this is from 3 to 7 of f of x, but negative. So from 3 to 7, everything is above the surface. Oops, 3 to 7. And so I'm going to write that it's negative because it's the opposite integral. And then I'm just going to use the formula for a trapezoid, which is 1/2 times the height times the sum of the bases, which would be 4 plus 3. So that gives me negative 7/2. Question 11 asks us to find the definite integral. So again, just as we did before, we're likely going to need u substitution. So 3x minus 2 is u, which makes this u squared in the integral. Du would be 3dx. In order for me to have 3dx, I would need 3, so I have to take a 1/3 to the outside. So that gives me 1/3, and then the integral of u squared du. But now it's not really going from 2 to 5, it's going from u of 2 to u of 5. But let's go ahead and integrate. So I've got 1/3, and then I'm integrating u squared, which gives me u cubed, that doesn't look like a 3, u cubed over 3. And now not plus c, but from u of 2 means use u and plug in 2, so 3 times 2 is 6 minus 2 is 4, and then u of 5 is 3 times 5, or 15 minus 2, which is 13. So now I'm going to take 1/9 and then u cubed, so 13 cubed minus 4 cubed, which gives me 1/9 of 2,133, which gives me 237. Now, you might be asking yourself, well, do I have to plug in u of 2? You don't have to. You can plug back in the 3x minus 2 for u. Just make sure that you're not sloppy with whatever you're writing for your limits of integration. If you write it as u, you need to change the limits of integration with respect to u. If you just rewrite it as, so basically you skip this step and you rewrite it as 1/3 integral of 3x minus 2 squared dx, then you can go straight, because it still fits the pattern, you can go straight to this, but with the u expression subbed back in. I don't do it that way, so that's up to you. Just make sure you're not being ugly about it, or I'll catch you with it. Same thing here. I've got u is 1 plus 4x. du is going to be 4 dx, so I'm going to need a 4 here, which means I need a 1/4 here. So again, I'm going to write this as 1/4, and then the integral of u of 2 to u of 6, which I'll find in a moment, and then this is u squared du. So that gives me the 1/4 that I had before, and then u squared turns into u cubed over 3, and then again, this is u of 2, so 1 plus 4 times 2, that gives me 9, and 1 plus 4 times 6, that gives me 25, so from 9 to 25. So my result is 1/12 if I take those two fractions to the outside, and then 25 cubed minus 9 cubed, which gives me 1/12 of 14,896, which gives me either a fraction 3724 over 3 just by reduction, or approximately 1,241.3 repeating. Finding the inverse of functions, remember I'm simply going to replace y with x and x with y inverse and solve for y inverse. So it can be fairly simple or more complicated. So this is going to give me x plus 10 is equal to 12 y inverse. Dividing by 12 gives me y inverse is equal to x plus 10 over 12. I'm going to leave it just like that. For b, again, I'm going to rewrite it as x is equal to 4 y inverse. How do I deal with that? Well, I'm going to take log base 4 of x and log base 4 of 4 to the y inverse. Log base 4 of 4, that's an inverse, it goes away. So I've got log base 4 of x is equal to y inverse, or if you want to write the y inverse first, you get log base 4 of x. Same thing here, x is equal to natural log of y inverse. And then I'm just going to take e to the x and e to the natural log of y inverse. E to the natural log, those are inverses and go away, so I get e to the x equals y inverse, or y inverse equals e to the x. Next, we're going to look at inverse trig functions and finding new trig functions. So my best advice is draw yourself a little picture like I have, and start with knowing how to use what's inside. So arcsine means if I took sine of theta, I would get 2x to the 9th. Well, sine is opposite over hypotenuse. So that's 2x to the 9th over 1. Cosine is adjacent over hypotenuse. Secant is like the inverse of cosine, right? So this is actually like cosine of 9 over x. So cosine is adjacent over hypotenuse. So know how to do that part, because if you don't know that part, then you can't do any of it. Now from here, I need to find the cosine of theta is what we're trying to do. So cosine of theta, we know would mean find b over hypotenuse. So we need to find b. So 2x to the 9th quantity squared plus b squared is equal to 1 squared, which is 1. So b squared is going to be 1 minus, I'm going to go ahead and square it now, so 4x to the 18th, which means b is the square root of 1 minus 4x to the 18th. So what is cosine of theta? Cosine of theta is b over 1, or just b, which is 1 minus 4x, square root of 1 minus 4x to the 18th. Again, same strategy for b. We have theta. We need to find sine of theta, so I need to find what is a. So to find a, I'm going to take a squared plus 5x quantity squared is equal to 1 squared. So a squared is equal to 1 minus 25x squared. So a is the square root of 1 minus 25x squared. So now I'm trying to find sine of theta, and sine of theta would be a over 1, or just a. So that's the square root of 1 minus 25x squared. And finally, I'm trying to find tangent of theta. And tangent of theta would mean I'd need a over 9. So let's go ahead and find a. A squared plus 9 squared is equal to x squared. So a squared is equal to x squared minus 81. So a is the square root of x squared minus 81. So now if I'm finding tangent of theta, I'm finding a over 9, and a is x squared minus 81, again, over 9. Let's find some derivatives now using transcendental functions. So for my very first one, before I even try to find the derivative, I would rewrite this as 1/2 natural log of x cubed plus 4. It's going to make it a lot easier. So now if I'm finding the derivative, 1/2 natural log of x cubed minus 4 tells me let's make u x cubed, plus 4. du is going to be 3x squared. So remember that if I'm taking the derivative of a natural log function, it's going to be u prime over u. So u prime, or du, is going to be 3x squared in this case, and u is x cubed plus 4 and plus c, but we forgot the 1/2, so I'm going to put the 2 right there. So now let's look at b. Remember, with exponential functions, we have u is 3x squared, we have du is 6x. So when I find y prime, it's going to be 6x and then e to the 3x squared. So you just have to include that derivative in there, kind of like the chain rule. Here I've got u is equal to 3x cubed, du is equal to 9x squared. So for this one, I'm going to include the derivative, 9x squared. I'm going to include the original function, 4 to the 3x cubed. And then because the base is 4, it's then times the natural log of 4. And for the last one, again, I've got u is 3x squared minus x. du is 6x minus 1. So for my derivative, my numerator is going to include du, which is 6x minus 1. My denominator is going to include both the natural log of 2, because we're in base 2, and the 3x squared minus x. Now we'll finish up with indefinite integrals. Again, utilize that u sub. So u is x squared plus 3, du is 2x dx. So make that a 2, make that a 1/2. So that gives me that f of x is, and again, this is now just 1/2 the integral of u, 1 over u. So we're going to use the natural log. So I've got my 1/2 from the outside, and then the natural log of the absolute value of u, x squared plus 3, and then plus c. For b, u is 2x squared, du is 4x dx. So I'm going to put a 4 there and a 1/4 there. So f of x is going to be the 1/4, and then e to the 2x squared plus c. For c, I've got a is 9, so remember these were the kind of trickier ones where you have an a and a u, so u is 10x, and then du is 10 dx. So this needs to be 10, so this is 1/10. So f of x is 1/10, and then we just have to find the one that fits that pattern, and that in this case is arcsine, and that's going to give me 10x over 9 plus c. And for our last one, a is 4, u is x minus 5, du would simply just be dx, so I don't need to worry about anything on the outside. So now I'm just finding the one that fits this pattern, and that gives me 1/4 arctangent x minus 5 over 4 plus c.